Hello guys, this is Josh. We just want to touch on the DSP exam preparation. I hope this video is less than 20 minutes, but I believe it's going to be worth it. Okay, straight to the point. We will talk about 8 things to remember, very important, and then we would flow through this DSP story, so to speak. It talks about the DSP module, how it is structured, okay, and how the past questions and the solutions are connected to the different parts of the module and different topics of the module. The reason why I've taken this approach is because as recently as about maybe 2 weeks ago, I understood some of these things, but and how they convert back and forth. If I really didn't, but but I needed to see a way that they interchange one to another in a way, especially like this, such that I can see, okay, we're talking about time domain here, we're talking about Z domain here, we're talking about frequency domain here. I needed to see how they are connected to each other. It keeps going back and forth. You need sample response, and you don't know where you are. You see. So it felt kind of almost confusing for me. So, but it helps when you see this way, that when you're changing from one expression to another, you know where you are. Okay. So that's why I've taken this approach, and it is helping me a great deal. So then we'll touch the past questions as we flow along the map like that, along the story. So I know it looks rough like this, but in a few minutes now, we're going to make sense out of all these. Okay, so let's get straight into it. Now, the things to remember. First off, let's start at the top here. So 8 things to remember. Number one, you need to decide ahead the questions you want to answer. It's going to be 3 out of 4 questions. That's what he said, I believe. So you should decide the question you want to answer ahead. Now, plan your time. Okay, just like the previous exams, hopefully. 2 hours, 45 minutes, take 15 minutes out. So it's going to be 50 minutes per question. Okay, when you divide that. And this time the questions are really going to be equal, so you could spend just about that amount of time in it. And I think this is a very short time. You have to know exactly what you're going to write and write it fast. You don't want to be guessing during that time. It's just going to fly. Okay, now this is critical. Change your calculator to radians now. Literally, like if you can do it right now, pause the video and do it right now. Okay, number 4, write out your past questions and answer for your one-sided A4. We're required to bring you one-sided A4. I'm not going to bring this into the exam. I might find a way to just do it somehow, but I probably will not bring this. I need something better than this. But anyway, your one-sided A4, I think, watch this, I think it should be the past questions and the answers. Both the questions, later questions, write the question and the answers, and you begin to swap variables, because all he's going to do is just to change a few numbers here and there. But you need to see the way the question was structured that brought about that kind of answer, so that when you see a similar question, you can easily map it together and change the variables and try to walk your way through. Okay, so write that out. Okay, I suggest you literally write it other than I was trying to print and type also, but it's better to write. Now, next, each of these points are very important. Practice many times, not just copying it many times. Practice it many times with the closed book. Close this your A4 and try to write it. You'll be surprised how many things you can or would have forgotten. Next, remember this formula. That's the first thing. Okay. But also remember, this is very funny. You remember that this minus b is also going to be divided by the 2a. Don't forget that. But remember the formula itself. You might write it down anyway in your A4 stuff. Yeah, then the rest is basically formulas. So digital frequency in radians is theta is equal to 2 pi f, given frequency divided by f sampling rate. Okay, then omega is also equal to 2 pi f. So remember that formula is not going to be given. Remember, as simple as this, it can be important. You used to make once or twice. Then this is for your, incidentally, it's going to be around the number 3D question. But anyways, also number 8 things, last thing to remember, is a set of formulas. And the first one is this one. And it looks a little rough, but you can write it out later. It looks a little rough, but it's this S. I think that is S is output somehow. Yes, iteration. The first one of the iteration output is equal to weight times input. Okay, S is equal to W times X. Now the second formula is taking this S into this is Y, which is another output again. Some of this concept I literally don't know them very much. I just cram it, you say. Okay, but this is another output. Y is equal to 1 divided by 1 plus e raised to power minus gain. Gain is going to be given times the S you got from here, and you move ahead from there to your C. C says error is equal to D minus Y, desired minus Y, okay? So error is equal to D minus Y. D is going to be giving you is usually 1, whole number 1, minus the Y you got from here. You see how it proceeds, you see? So r to d minus y. Then your fourth thing to remember here, okay, is w new, that's the new weight, is equal to the old weight. These two are usually matrices like this, okay, times n is learning rate, nex, e is the error, you see, and x is the initial input you worked with here. So you flow from s to get wx. These two are given. From you take the s, you put in this equation to get your y. You take your y, put in this equation to get your error. You take your error, put it into this equation to get your new weight. Okay, it might ask you for 2 iterations, so I think you need to run through that a second time. All right, so well, we're not touching the calculation yet, so that is 8 things to remember. We've done that in less than 8 minutes. If that's all you watch, I tell you, it's going to help you, and you put it to practice, of course. That's going to help you. Okay, but there's still more things ahead. You might want to stick around. All right, so let's start the story, the DSP story. DSP is digital signal processing. Trust me, it's not going to be boring. I think it's going to be worth it. Okay, so it's digital signal processing. It's about taking analog signals like the train sounds, like voltage, like wind speed, things that are analog, and converting them into digital signals. Okay, that's what it's all about. And to do that, you do what is called sampling. This is your question 1A, you see. And when you sample above the Nyquist rate, that's what is required for you to do. 2 times the frequency of the analog signal you're trying to work on. So that little theory is going to come out around there, possibly, just like it did in the past question. Yes, so you need to sample above the Nyquist rate, which is 2 times that frequency. If you don't do that, you're going to have aliasing, whatever. Okay, so to avoid aliasing, you need to sample above that. And you have that funny diagram, that wave stuff, that's that. Then when you do that, you get your discrete signals. Now, should we go up or down? Okay, yeah. Well, let's continue the journey first. We'll come back here. Yeah, so discrete signals, well, digital and discrete is slightly different. The quick difference is for a signal to become digital, it has to be first sampled, it becomes discrete, and then it becomes quantized. You quantize the discrete signal to give a digital signal. I think that's what that is, but that's just by the way. So then there are some signals that are linear, there are some that are non-linear, but we're talking about the linear ones. Now this takes you to your 1C. That's why I took this route first. 1C, what does it take? An engineer wants to know if a signal is linear or not. Okay, he needs to find out that if x of 1 is equal to this. I need to show you that question. You see, 1C, that's where we are at. Now, this is a generic question. It's not somewhere in our journey, but it's not something too difficult to get if you understand the principles. So this is where we're at. Okay. Yeah, so this is where we're at the question 1C, okay? He needs to just run the story, okay? He wants to know if the system is linear. That's what he's trying to do. Okay, so then we have this, okay? So that's that equation that you write to prove that the system is linear. It's just some story. Now, apart from linear systems, there are adaptive systems, and that's your question 3D. We're going to touch that later. So let's move on along the path to, yeah, so now there are linear time invariant systems, linear time invariant systems, or linear time invariant discrete systems. Now there is a way, now this is where it gets interesting and it begins to branch. Okay, there is a way to represent linear time invariant discrete systems. See, these are the different forms of representations of linear time invariant discrete systems. Okay, these are different ways to represent them. This is where, for me, the confusion almost kind of started, but now it's resolved. Okay, so let's see. Yeah, so these are the 3 ways, 1, 2, 3. Okay, now you see an LTI, a linear, let's just check it quickly. A linear, an LTI, let's just do it quickly. Control F. LTIs, did it write it like that? No, but linear time, so it pops up about 3 times, you see. So a linear time invariant system, blah blah blah, that's your 1D altogether. See, straight up. Next, a linear time invariant, it keeps saying that, and you wonder where is that coming from. Next, this should be one more. Is it hanging? Yeah, the input to a linear time invariant system. So you see, it pops up many times. You see, and yeah, this is another one. So it pops up about 4 times in just one exam. See, it's as good as once per question, something like that. Okay, so that is what it is. It's a story came from here, and it came into this side. So just keep following like that to help you understand where to place things as you work through. So So linear time invariant discrete system representation, there are three ways to do that. There is a frequency domain, there's a Z domain, there's a time domain. The Z domain is the main one called the transfer function. There's a frequency domain, frequency response. You see all these terms when you see me bracketing like this and underlining it, you see them in the exams. So you understand where this thing is coming from. You will not see this word very much, but you will see these ones like this. You see this difference equation. You see that. So the main one, the main representation of a linear time invariant discrete system is the Z domain, the transfer function. Okay, now there's another way called the frequency response. There's another one called the time domain, and that time domain is divided into two. You have the linear control coefficient, well, that's a long name. You have the difference equation. You see this popping up also, and you see the unit sample response. Okay, these are the two ways. Wow, this picture is somewhere. I think I've got enough. But it's this. I didn't just make this up. I'm probably I'm probably not smart enough to make this up myself. This is this 1, 2, 3, 4, and these two are in the materials somewhere. Now there's a ton of materials, and he was not very organized with it. Okay, there's a ton of them. You don't want to start going through that. Okay, see, that's some of them are the same, some of them are condensed, some of them are it's just, and these are all different materials. You don't want to do that. But long story short, one of those materials has this branching. So I just crystallized, just did something around that to broaden it and do all of that. And I began to see how our questions are connected to that. Okay, I need to unlock this so I see what's going on. Okay, so let me see. By the way, if there's anything I'm not saying right, then just drop comments and all so we could check it together. There's still time for that. So now, when you see this transfer function, is usually around Z. Is a Z domain, isn't it? Yeah. So anything around Z, all the calculations you see around here, this part of this whole picture, around here is the Z domain. Anything around here is the frequency domain, and to have this is the logo of the frequency domain. This is the logo of the Z domain. See this? Okay. The time domain is divided into two. Is something called the difference equation. It will look something like this. Okay, and there's something called the unit sample response. It's going to look like this. Okay, so don't forget the frequency domain looks like this, and they're interchangeable to each other, these four. Okay, now therefore is 1, 2, 3, this 3 is divided into 2. So this is the frequency domain. It's transferable, it's convertible into the Z domain. Z domain looks like this, anything Z like this. Okay, and then this is also transferable, convertible into the difference equation. The difference equation looks like this, and then it's also, you could also look for the unit sample response. It looks like, that's the weird one if you ask me. You see, it looks this delta n and delta u raised to the power. Wonder what is u? Honestly, I don't know. I don't care. I just want to pass my exams and move forward. Okay, so this leads you to the 2a. Now I wrote stability here. Okay, it pops up here and there. It pops up somewhere around 4D or 4B also. Okay, stability is basically, of course, you know that when you have an equation like this, you want to check the stability. Stability, what is that? Stability, remind me. Stability, yes, you find the poles, you find the roots, yes. Stability, yes, you find the values that make, most of you know it already anyways, but what makes this equation equal to 0, you equate the numerator to 0, then it gives you the zeros, and then you equate this in the denominator to 0, it gives you the poles. Okay, so you check that, and if they're in the unit circle, blah blah blah, you know that probably. So that's what stability is about. That's in your question 2A1. We're still going from 1 to 4. Okay, so we'll probably exceed 20 minutes, but I hope you're realizing by now that it's worth it, especially if you have not. If it's not something you have a background in. I don't have too much of a background in it. I have a little bit, but not too much. Okay, so let's go to question 2A. That's 2A. I asked you for stability. 2AII is this. Now let's see what 2AII is and see how it flows along these arrows to achieve this. 2AII says a discrete linear time invariant system is represented by this. Oh, by its frequency response. Okay, you see that popping up, so you know where you are on the map. And this is the frequency. Okay, so using the suitable diagram, determine whether the system is stable and justify your answer. You know the answer to that. I'm not going to go through that. So go check the answer, how it is done. Okay, now 2. Obtain the system difference equation and determine its unit sample response. Obtain the system difference equation. Okay, difference equation, and obtain and determine its unit sample response. Assume that this and this and this is that. Okay, so obtain the system's difference equation and the unit sample response. So you need to go from here to here and here. Okay, yeah, so that's what you need to do. Yeah, that's what you need to do. So that's why this is there. So now we took that to get here. Incidentally, you need to go through here. I mean, somehow it just works out that way. It works with this our map. So you cannot. I don't know if you cannot, but the way it was done in the exam is you had to go through the Z domain to get to the difference equation. Okay, so to get from the domain, frequency domain, into the Z domain, this is what you need to do. You just change your e raised by j theta to Z. You see, that changes to that, and then you walk through this. Let's zoom a little bit. You walk through this. You divide through by Z squared. In case you don't know what happened there, we're working on this question. Divide through by the highest power of Z, which is Z squared in this case. And you have this, and from that you cross multiply, you arrange, you get this. Now this now changes to this. Okay, when you get this, it changes to this. How does this change to this? I think it's just by looking at it. This is your difference equation, by the way. Just looking at it, 0 to yz, z raised by minus 1 becomes y, small y, n minus 1. Z minus 2 becomes y of z minus 2 becomes y of n minus 2, like that. So this is your difference equation. You just look at it and you map it together. The same way you looked at this and map this together. Okay, now how do you get the unit sample response? I've not done that because that was not done here. Okay, because I think that's what that 5 marks is for. This other 5 marks is for this difference equation. These 5 marks is for this. Excuse me. So that's that about 2a. So let's go to 2b. A system is represented by its transfer function. Okay, what is transfer function? Z domain. You see, 2b. A system is represented by its transfer function, which is this, is Z domain. Okay, so we're using the real life examples to touch on it. So where is the transfer function? This is it. Okay, obtain an expression for its unit sample response. So we're going for transfer function to unit sample response. Let's see if we'll go through difference equation to get there. Let me see. Or is it this? Okay, so let's see how that is done. So you take this. The first thing it wants you to do is yes, factorize the denominator. Okay, you factorize it, you get this, and you divide this. Now this is slightly tricky, but just stick with it, you'll get it. Okay, so factorize this. There's a little trick about factorizing decimal places. What you might want to do, listen to this please. Put a 0 behind this 0.3, becomes 30. Put a 0 behind this 1, or maybe not. In this case you don't need to, but it's still correct when you put a 0 behind it. So it is that kind of 30 that became this 6 and 5, such that 0.6 minus 0.5 became plus 0.1. But this 3 can be deceiving. If you put a 0 behind it, if it's a decimal point, of course, then it helps you to easily find the factors from your head. Okay, so you divide by h, divide by z. Okay, because this a wouldn't have a denominator when you do the partial fractions. So do this and then divide by z. So substitute a for a, substitute z equals 0. For b, substitute z equals minus 0.6, because this 0.6 goes to the other side. For c, substitute z equals positive 0.5. So how do you do that? You take the numerator, divide it by z. The whole thing divided by z gives you this. Okay, you substitute for 0. 0 plus 0.6 is 0.6. This becomes minus 0.5. Don't forget z is 0 for a. Okay, and put 0 here. When you simplify that, you get this. Do the same thing for b, but when you have this equation for b, you have z left. This denominator will be gone. You have this. That's the first thing. Second, your z is going to be minus 0.6 for b. So you put this is gone. 0.6 here, 0.6 here. Then you do that. You have this numerator. Okay, you get this for b, you get this for c. Now this is going to give you basically three parts of the expression this way: a, b, blah blah blah. Just put what you've got into this, and by taking, now watch this, by taking the inverse transforms from tables, whereas the tables is here, is somewhere down there. I don't want to take too much time in this video. So where is that? Well, you guys know where it is. I don't need to bother myself. Yeah, something like this. See, so use this and check it to each other and see how it makes sense to you. Okay, that's why we had to put a minus here, plus here first, and put a minus here, so that you can look like whatever is here. Okay, so you're taking inverse transforms, inverse transforms, inverse transform, like that, and from the tables you get this. So we didn't necessarily go through difference equation. Okay, so we get this. So 0.67 remains, but it has this weird thing I told you. This is weird. delta n minus 0. Da, 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 minus 0.6, like that. Okay, it's going to look like that. Just check the tables. Where is it? Okay, there's a, well, this is it. Yes, I'm correct. Right? Yeah, this is it. Yeah, this is it. So just check these tables for this, the partial fractions that look like this. Check it. You have all this weird stuff, right? Yeah, that's the a delta n there. So you have this. Okay, so that's that. So next, that is 2b. Now let's go to 2c. Given this, let's read the question quickly. 2c. Okay, so excuse me. Yeah, this is 2c. So the input to a linear, that name again, system is this, and you have a system's unit response is this. Okay, you have unit response. So obtain the expression for the output. All right, so that's x. That is your x there, and that is your hn there. Okay, given this and the system's unit sample response, that's the name there, is this. Find y of n. Generally, this is always the case. Okay, but first we'll take it to the z plane first. Actually, in this case, we need to take it to the z plane. There's no space here, so I can't put it, z domain rather, I can't push it into here anymore as much. So, but this is what you have. Now this you obtain just by looking. Is it just by looking? Yes. Now I don't know why this is this simple. Okay, I hope it is correct and not an error, but just by looking at it, 0.8 dn becomes 0.8, 0.2 dn minus 1 becomes this, and I think it's correct actually. Okay, and 0.9 becomes 0.9, 0.9 dn, that becomes that, so this becomes that. I think you can't multiply like this in this domain, this unit sample response format. It's probably going to be wrong. So it's taken to the z domain. Now you have simple expressions. You just multiply them through, and we jumped this big river here. So we jump from here, this multiplication here, over down here. Okay, and we continue our arithmetic, and we have this. Okay, z, right? And taking inverse transforms by sight, literally just looking at it. Again, we didn't need to go through this route. Okay, we just look at it and it was easy to do. I think it's the same thing as this, the table down there. Yeah, so just by looking, we get this. So yn, this yz becomes yn, which you're looking for. Okay, then 0.2 becomes 0.2 dn, just like we did, just back it up. 0.74 becomes this, 0.14 becomes that. Okay, and this is what you're looking for. That's your 2c. Let's run. So basically we've finished all this. You see, all these complex things now is beginning to make sense. See, so now where is 2d, 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 2d? There is no 2d. So let's go to number 3. Okay, now number 3, 3a. Okay, now we can go to this bar on the map. Some digital signals. Talking about digital signals, there is discrete Fourier transforms. You have, that's DFTs. You have magnitude and phase power spectrum. You have issues affecting spectrum analysis. Okay, just like short-term Fourier transforms versus magnitude frequency spectrum. All those kind of story. You're gonna find them here, 3A and 3B. These are theoretical questions. Okay, so what is the difference between this and this and that? They are under this topic. Okay, branching out from digital signals and talking about these transforms and blah blah blah. So that's 3A and B. Leakage. Okay, spectrum leakage is an issue, just like spectrum leakage, spectrum analysis. Okay, 3C. Let's go. The signal is this. Okay, and is defined for this range. The sample is 1000 per second. Determine the DFT, the discrete Fourier transform. Did we solve that? 3CI. Did we solve that? Well, yes, we didn't solve it here because I think it's pretty simple. So let's look at the solution of 3C just quickly. You probably already know that. Yeah, 3C. So you have this. Now, yes, there is DFT. There is a table for DFT. This equation was gotten from a table here. Okay, let's see if we can find out. This should be here. This, yeah. So this, figure it out somehow how to get it. Now, is there anything complex in it that I might help someone with? I don't think so. I think it's pretty straightforward. Now, n is equal to 3 because this is talking about n minus 1, and it's saying this is something that someone might not get. Okay, it's saying from 0 to 2 in the question. and this requirement says n minus 1 is where it should end. So if it's 0, 1, 2, if 2 is n minus 1, then n is 3. That's how 3 was gotten, in case you don't know that. Anything else complex here? I don't want to take too much time on this video. Anything else complex here? That is difficult, I mean. No, I don't think so. There is a general formula to convert e raised by j theta into cos theta plus sine theta, so that's what they're using here. And anything else? No, I don't think so. I think it's pretty straightforward. Is there any mistake, typo there? I don't think so. Alright, so that's that. I think it's fine. Then this is just a simple formula which you need to remember, maybe. Harmonic separation is equal to 1 over nt. Now that's probably another formula you should add to this. Maybe it should be your number 9 thing you need to remember. Okay, so that's that. Components is 0. Now I think there's a little mistake here, which is let's see. Yes, there is something here, which is that in the question, now you see where you get your formula from, the discrete Fourier. In case he asks for inverse discrete, this is what you use. Or if he asks for Euler's, which I don't know, but let's hope it doesn't. So, but let's go back to 3a. Now, it says, now watch this please. It says the signal is x equal to 1, 2, 1. That is where you got these, this 1, 2, 1 is where you got this from. is where you got this from. This 1, 2, 1 is where you got these substitutions. Weird. So yeah, this 1, 2, 1 from x of 0 is 1, x of 1 is 2, x of 2 is 1. That's where the 1, 2, 1 came from. Okay, so that's that. Let's go back to our map. Let's see. So that's your 2, 3C. Are we there yet? 3C, yes, that is 3C. So plot his power spectrum. That is what it did here. This is the power spectrum, which I think is it's probably not correct because of the mistake he made above there. Okay, so next, that's 3C. So now 3Ds is ALC, okay? So now this is 3Ds. Now this is where you use the formula. Now let's run it. So you're given a lot of variables. Don't feel confused when you're given a lot of variables like this. All of them are supposed to help you. They're not to confuse you. But if you have this flow in your mind, this flow of formulas, A, B, C, D, if you have this flow of 4 formulas in your mind written somewhere in your A4, don't forget, if it's written there, this 4 flow of formulas, you will just simply slot those variables into it. Except maybe for X that was transposed here. Here it was a 1 to 3, and here it became a 3 to 1. Where is it? It was vertical here and it became horizontal somewhere, if I get it right. So that's just about the only thing. But anyways, all of that will be given. So an ALC is a part of the system. The feature vector is this. Oh yes, it is flat here and it was transposed in the calculations. Represent an example of an object from category A. Desired output for the ALC is 1. The initial condition for ALC is weight this. Activation transfer function sigmoid. I think this sigmoid forced us to use this formula. This is the sigmoid formula. So if you had said something else, this formula might change. If you say something else, I don't know what to do. But let's see. So yes, that's the sigmoid. Yeah, so the weight is this, and the activation function this. The function sigmoid is gain is this. The bias is 0. Learning rate is 0.8. Okay, so just start with the formula. S equal to WX. What is the weight? Weight is this. What is the X? X is that. So multiply the matrix. 1 by 3 is like that. So 0.3 times this times this, 0.9 times 0.2, 0.1 times 0.5. You get this, and you add it together, you get S. Like I said, S goes into this equation. Put S here, e raised to this, you get Y. Put Y into this equation. Desired value is 1. Okay. Put Y into this. That's 1 minus Y. That's 0.49. That is your error. Okay, good. And you take your E into this. Okay, that's the last step. W new, you don't know it. W1, 2, 3. This W old, you're given that already. That is this. Okay. This. Okay, then. Yes, then 0.8. Where is that coming from? Plus 0.8 is the learning rate. It's given there already. 0.8. There we go. Yeah. Then 0.49 is E. What is E? Error. Yeah, 0.0409. Yeah. What is your X? X is this. It's transposed. Okay, it's flat here. And it could be because of typing. There's no way to make it vertical. I don't know. I don't really care. So you have 0.3, 0.9, and 0.1. So like that. Now watch this. You multiply these two together, no issues. This is ticking because the same thing down here, same thing down here, no space. So multiply these two together, you get this. Then multiply this by each one of in the bracket, you get this. So you have this equals this plus that product, and you add them together, you get this. Boom. Goodbye. Next, digital filters. Where is that in this map? Where is it? Four. Where is question 4? It's a dangerous stuff. Yeah, I don't like it very much. That might be the one I might not answer, but if you know it, please go ahead. So 4D talks about filter. You have Butterworth, infinite or finite impulse response. That's IR. They have stability stuff too, but it's the same calculations of stability where you check denominator and numerator. And that is your 4A. So it talks about Butterworth. Talk about strength as a theoretical question. And what's this? Low pass describe function. Yeah. So yeah, justify stability. That's stability. So this is transfer function. Okay, it's talking about transfer function again. It's a little connected, but now you have a slightly different kind of X. Okay, so determine the filter's output when the signal is this. That is C. Now they did something here. They equated S to equal JW in the calculations. The reason why I am not sure. So that is probably a number 10 thing you need to remember. Okay, I told you about number 9 the other time somewhere. So you need to remember that when you're in this domain, in this filter stuff, for that particular kind of filter, S equals JW for some reason. I don't know. So where is that? That is the stability stuff. So that's it. You see, you need to evaluate the frequency. Let's see. So S equals JW somehow. So this is just expanded. You know this is your frequency just by 2 pi omega f. You know this is your frequency. You work with that. Equated S equals JW. Your W is now inserted there. Then everything else flows from there. Okay. Then you just mapped y, x, and y somehow, and you put this 0.5 instead of 5, and you get that. Now this again, like I said here, you need to use the appendix a lot in number 4. Low pass, high pass tables, substitution of and formulas. You see, so you have to go and look for 4Ds asking you for Butterworth. So you need to go to the bottom of this and go look for Butterworth. Butterworth. Yeah, is he here? Yeah. So you take this guy and you go dump it. Don't let me make it sound unattractive. It can be very easy. I've done it really, but I don't know what Dr. Reza yeah might want to do to twist things. I don't want to. That place is slippery. I don't want to fall. So, but it's not bad. If you know it, you know it. You see. So that is where that funny equation was gotten from. This one is from that table I showed you. So you go through that, then you use whatever to transpose from low pass to high pass. What did he do here? I don't know. I'm not sure what it did here, but I think I've got it. Okay, I'll show you my notes somewhere. Just look somewhere around here, you find it. So I think that's what it did. Then finally you have this. It just divided by s squared. Watch this. It just multiplied numerator and denominator by s squared. Boom, boom. You have that, and you have this. From this, it went ahead to do this. And there is, watch this, there's a mistake here. Okay, as far as I know, it's a mistake. So what it did was to divide the numerator and denominator by z plus 1 all to the power of 2. Okay, so if you have a question about this also, you can let me know, but a lot of people probably have figured it out, but it's not like it made a mistake here. That's why it's looking like it's not making sense. So that is the end of the story. So now we've covered literally everything on this map. So if there is going to be a second video, I have seen some questions that may be the literal questions tomorrow. I've not really studied them myself, but I could extract them from some of this ton of materials which are not properly labeled. Okay, they're not properly labeled. So if there's going to be a second video, it's going to be on that and mapping these topics. We're just going to bring about possible actual questions, but if you get the principle, I think we're good enough. Okay. So I'll just bring about 3, 4, 5 of them. That might be our second video, or maybe just a picture screenshot. Okay, thank you very much, guys. It's been nice talking with you. Goodbye. Thank you. Bye.